Let's talk now about how we came to know so much about this universe of ours. And to start with, we will be talking about the early science, which will prove to you, I hope, just how darn difficult it was to just figure out which revolves around which, that is, Earth or the Sun. It's just to start with this discussion. So we're going to keep things rather short and only point out some of the most important milestones. So if you need more details, please check out the textbook. The chapter is beautifully written, this chapter number 3, just like the rest of the book, especially if you ask me. Okay, so I think it's important to note that the roots of science stand with the Greeks, whose knowledge was preserved through history. Well, there were hiccups in that preservation, like, for example, the fire that enveloped the Library of Alexandria and destroyed so much of what was preserved there in terms of science papers, notes, evidence of thinking at a time, etc. So again, please read in the textbook about this. It's an important historic moment, especially in the history of science. But it is important to acknowledge that the Greeks were the first known to make models of nature, who tried to explain patterns that they observed in nature without resorting to the myth or the supernatural. So, for example, they came up with this geocentric model. Geo means Earth. Okay, so the Earth is here in the middle. And that Earth it has a lot of circles, perfect circles as they call them, that would represent the orbits of pretty much everything we see on the sky. So, science at that time was heavily blended with philosophy, communication, or pretty much everything that attempted to answer questions like, why now, why here, why me? And some of the very first models of the universe, and of course the universe is in quotation marks here, as at those times the humans did not know much about what could be outside, say, the sun. It was just, things you can see basically with the naked eye, right? So some of the first models of how the world looks like consider the Earth at the center of everything, right? Geocentric models. As you can't deny it, it is actually a pretty accurate description of what we observe by just looking around once, or maybe even more than once. It takes actually a lot more than observing once to figure out some of the, the ways in which things actually happen. All right. Also, all things out there seem to be perfectly round based on some calculations, and they also made sense, as we will see in a second, like the Earth itself, and then the specks of light that were moving around us, like on the sky. So the idea of perfect circles or spheres were actually pretty prominent, and why not at a time? Take, for example, Eratosthenes, math, philosophy, what's there? Anyway, he was the one known to have recorded some of the very first calculations of how big the sphere we live on might be. The method is pretty ingenious, so it's definitely worth taking a look and understand how he did it. So he realized that the sun is exactly at noon time, that is lunchtime, right? He was outside looking around, observed the sky, and the sun was straight up when he was in the city of Syene. All right, but when he did the same thing at the same time during the year, say maybe not a year, just the same day, the same hour, right? He realized that the sunlight was coming from an angle of about 7 degrees relative to the straight up line, the zenith, if you remember, right? Straight up. Okay, so this was the sun, and it was this tiny little difference. I mean, it's not that tiny. It's significant. He could measure that. So he put together a scheme like this one here, and with the assumption that the Earth was round, that is spherical, he realized that he can calculate the circumference of the sphere by basically matching this angle, right, of 7 degrees with the arc length on that circle. So he said 7 degrees correspond to basically the distance between Syene and Alexandria. All right? Okay, but we also know, and he knew, they were pretty good at geometry. They actually invented it, right? So he knew that, this kind of angle, which is 360 degrees, should correspond to the circumference of the Earth, right? Okay, so in case you didn't know, ratios are, your best friend everywhere. So with this correspondence, then the ratio 7 to 360 must equal the ratio between distance between Syene and Alexandria to the whole circumference of the Earth. All right, so basically now solve for the circumference of the Earth, and you actually get this thing, right? Circumference of the Earth is going to be 5,000, which is, this is multiplied, all right, which is distance between Syene and Alexandria, okay, multiplied by 360. You can cancel the units, okay, right, and you get the total, and of course the units are whatever they used for distance, which is stadia, the plural from stadium, right? So they didn't use, so that's the distance between Syene to Alexandria, okay? So no miles or kilometers at the time, just a different unit. And given the information we have about the type, the length of a stadium at a time, and compare with the modern values, so we get that this many stadia actually correspond to, given that Greek stadium is about a sixth of a kilometer, we get actually a pretty good estimate of the circumference of the Earth. So hey, pretty good with just some ingenuity, looking at the sun basically, right, and measuring by eye angles of a few degrees, right? Okay, but the scientists kept observing the universe, the world, everything that was out there, especially in the sky, and they realized that there were some things that did not seem to match nicely the models that were circulating at the time, and in particular this geocentric model of the universe. Remember, the model in which the Earth was at the center of everything else was revolving the Earth. And one thing that posed some problems were some of the planets. Actually, the word planet, right? That means, that is the word for wanderer in Greek. All right, so there were some of these specks of light that were moving actually more than others. So the other ones were called stars, but these ones were just stars that were wandering around. So it wasn't that the ancient Greeks knew that there was a physical difference, a very important difference between the planets and the stars. So they had names for those wanderers, the ones that were actually visible with the naked eye. Were Mercury, the one that's very close to the sun, so it's always visible at the dusk or dawn, right? So sunset or sunrise, just after the or before the sun is under the horizon, okay? And then it's Venus, which is very bright when visible, again, still very close to the sun. So it's either a morning or an evening star because of that situation, right? So you probably remember when we talked about eclipses, that would be pretty much the only time you get to see Venus in the middle of the day or some other time of day, right? Otherwise, it's only in the morning or in the evening. And then Mars, which was noticeably red, and then Jupiter, which is actually very bright, being a really large planet, and then Saturn, which is also in this beautiful image, and it's actually much further away from us than Jupiter. But see how deceiving this picture might be. All right, so these were the planets known in the ancient time. Okay, the thing is, they posed some mystery. Okay, well, they usually moved slightly eastward from night to night. It turned out that for just a few weeks at a time, they went in the opposite direction. They went backwards. Okay, after which they turned back to the usual regular direction. So here's an example of what Jupiter's position looked like in the sky, right? So this is in June, and it keeps moving, right? Just the next few days, you take a picture, and it's not in the same locations. It moves like this, and then, right? It moves, and then it seems to go backwards for a few weeks, after which it continues back from the initial direction of motion, which was eastward, right? Okay, so that's why this motion was called retrograde motion, and we added later on the word apparent because that's what it is. It appears to go backward, and we actually know that we can explain that now. Okay, now because we know exactly what they're doing. What they do is we as Earth, we lap another planet. For example, here in this diagram, so here's Earth's orbit and then Mars orbit, and both of these planets are going in the same direction around the sun, right? And you see how at some point, say day 1, you're seeing Mars here, but then day 2 you see it here, so it's going nicely eastward in day 3, and then while Mars continues, right, so 3 and then 4 continues to go in the same direction. There is no change in its direction of motion whatsoever. In the sky it appeared to move backwards for a few days, after which, because the projection in the sky gives that impression, right? And after that, starting with the 5th observation, the planet seems to come back to its senses, so to speak, and move again towards east. All right, okay. But the thing is, this situation is actually very difficult to explain if you think that Earth is at the center of the universe, right? And in fact, it's worth noting that the ancients considered but actually rejected the correct explanation. Okay, so to be fair, the ancient Greeks, did consider both of these possible models of the universe. So again, Earth is at the center of everything. Helios is the Greek for sun. Okay, so the sun is at the center of the universe. So we have two different models that they considered, and in both of these models, the orbits were circular. But they did have different things at the center. So here was the Earth at the center. In a heliocentric, obviously the sun was at the center. The stars were fixed on the celestial spheres, and the planets, all of them, and then including the sun and the moon, would orbit around the Earth in the geocentric model. Everything was orbiting the sun. All the known planets, or the wanderers, were actually orbiting the sun, but the moon was going around the Earth. So these were the possible models that kind of circulated at the time, but it turned out that they could not reconcile mostly with one particular thing that is called stellar parallax. So when we talk about the stellar parallax, let me tell you about the parallax. All right, so here's a tree that is in front of the mountain, and you are driving a car and you're looking at the tree, right, while you're here, and this is what you see, right? If you were to take a picture, this is how it's going to look like. You see the tree on this side of the mountain, but later on, so you travel quite a distance and you look back at the tree, and it's going to look like the tree is not where it was before. It shifted, right? Now you can, let me tell you about another little experiment that you can do. Just keep a finger in front of your face at arm length and look at it with one eye at a time, all right? What you should be able to notice, okay, is that the finger shifts relative to some background, say in your room, okay? So that shift in itself is called the parallax, right? It's an angular shift, but that is important, right? So now let's apply the same concept. So the Greeks knew about this. They were very careful observers of the universe at the time. They knew about this effect, and so they thought, hey, if Earth revolves around the sun, then we should be able to see some of the nearby stars shifting in position relative to the background stars, right? Especially if we look at them some time apart, giving us, quite a baseline difference between right, left eye, right? And then we have the right eye here. You look at that nearby star, and sometimes you see it in this position relative to distant stars, and you would see it if you look at it in January, you see it shifted, right? Okay, so that was the prediction, and it makes a lot of sense. It's based on observations that you can run, anytime you can think of, right? Even in your room, okay. And the thing was, there was no shift to be seen. All right, they were unable to observe this stellar parallax. Now, what could be the reasons for that? So one is the stars are just so far away that the stellar parallax is just so So small, too small to actually notice with the naked eye. There were no telescopes at that time, all right? Or the Earth actually does not orbit the Sun, right? Because the Earth is the center of the universe, and so, that image does not apply, okay? So we do know now that this is actually true. We do observe parallaxes nowadays, but with telescopes. All right, so it was really very hard to believe that the stars could be that far away that this parallax would not be observable. All right, okay. So then, of course, people needed explanations of this phenomenon of retrograde motion while having the Earth in the center of everything. Again, the geocentric motion. And Ptolemy was one of the scientists that came up with a model that tried to explain as well as possible the positions of the planets, especially during the apparent backward motion that appeared on the sky. All right, so Ptolemy made some calculations and showed that if these planets were actually not revolving around the Earth themselves, but they were on circles whose center was revolving the Earth, right? Then at some point they would look like they were actually moving backwards in the sky. So that actually resembled really nicely, and down to some inaccuracies that explained actually pretty well that retrograde motion at the time. So that circle upon circle model, okay, explained fairly okay what was observed with these planets. And I say fairly okay, but then hey, with more observations of the motions and positions of the planets in the sky, it was found that the model, needed to be more perfected, needed to be adjusted. And so what happened, was like, Ptolemy actually had to include another circle, right? So it said, okay, this is the planet that was moving on a circle whose center was on another circle whose center was on the big circle, and actually ended up, this Ptolemaic or geocentric model ended up having many epicycles. Or circles upon circles upon circles upon circles. So it was, as it was actually recognized at the time, and it still is, because it's a very complex compilation of calculations, geometric calculations of the positions associated with this circle upon circle upon circle, the Almagest. Or the greatest compilation at a time. That's the Arabic for greatest compilation. It's very, very complicated model, which worked enough to actually remain in use for about 1500 years. So that's where we were at the time. So now if you meet a question like this in homework set or the exam, that asked, how did the Ptolemaic model explain the apparent retrograde motion of the planet? You would immediately recognize that we are talking about the geocentric model, okay? And then you read the answers. So A would be, the model showed that the apparent retrograde motion occurs as Earth passes by another planet in its orbit of the Sun. Well, this is true, but in the heliocentric model. So not true for Ptolemaic model, right? So that is not going to be the answer. This is not how Ptolemy explained the apparent retrograde motion of the planets. Let's see B. The planets resided on giant spheres that sometimes turn clockwise, sometimes turn counterclockwise. Well, we never talked about that. Okay, maybe they considered, but it was definitely not a model that was seriously considered. How about C? The planets sometimes stopped moving and then reversed to move backward along their circular orbits. Again, maybe some of their first thoughts were maybe that's happening, but there was no good model that would explain that. So that's definitely not how Ptolemy explained that. How about D? The planets moved along small circles that moved on larger circles around the Earth. So yes, circle upon circle model. So this is it. All right.